I'm hoping you're relatively familiar with the pH scale. You've probably been told the pH scale goes from about 1 to 14, although we can have pH values in the negative range. That would be acceptable if you have a very concentrated acid. To calculate pH, we're going to take opposite log of the hydrogen ion concentration, or you might also see this written as hydronium. So it might be like H3O plus. Same thing. Whether we write the hydrogen as attached to a water molecule or free floating, the value of that concentration is going to be the same. I've probably done that in the past. I'm hoping you've done that in the past. There is something called the pOH, which comes in handy. It's the opposite log of the hydroxide concentration. And if you were to add the pH plus the pOH, you should get 14. It kind of comes from this. Here's another equation that's in the packet, and it wouldn't be such a bad thing to jot this one down too. If you take hydrogen ion concentration, or hydronium, times hydroxide concentration, that should always give you 10 to the negative 14th. Now, we kind of looked at water. In a pure sample of water, the hydrogen concentration is 10 to the negative 7th. It was experimentally determined at 25 degrees. There is 1 times 10 to the negative 7th moles of hydrogen per liter of water. And the same for hydroxide, experimentally determined 1 times 10 to the negative 7th moles of hydroxide. So obviously then if I multiply those, I get 10 to the negative 14th. And if I add the pH and the pOH for water, I would get 14. Well, this will be true of any solution. If the solution's more acidic, there's more hydrogen, less hydroxide. If the solution's more basic, there's less hydrogen, more hydroxide. But the product should always give you 10 to the negative 14th. So a couple things we can do with this. We want to calculate the pH and the pOH of the following solutions at 25 degrees. I believe your study guide lists this as not 1.0, but like 0.1 molar. So we'll do the same. Okay, if you have the hydrogen concentration, this is a piece of cake. pH equals opposite log of that hydrogen ion concentration. You could say 0.1 molar. And again, it could be hydrogen or hydronium, H3O. If we plug this into our calculator, we get opposite log 0.1, a big fat 1. Well, you maybe did that in your head. Because if I were to put this in scientific notation, I'd be looking at 1.0 times 10 to the negative first. The log, L-O-G log, is just the exponent of 10. As long as there's a 1 in the front, 1.0 times 10 to the whatever. The log is that exponent, and pH is opposite log. Oh, so if the exponent's a 1, pH is, or negative 1 for the exponent, the pH is 1. Manageable. Other options then, you want the pOH. You could do this. pH plus pOH equals 14. So if I know the pH is 1, the pOH is 13. Indirectly then, what if, and they don't ask me this now, but what if they said, what is the hydroxide concentration in this solution? Well, if we know pOH is opposite log of the hydroxide concentration, we could just say then, obviously they're not asking this, but the hydroxide ion concentration should be 1.0 times 10 to the negative 13th moles per liter. And that's kind of what it means. The pH or the pOH is referring to the opposite exponent of 10. So if your pH is 1, the concentration is 10 to the negative first. If the pOH is 13, the concentration of hydroxide is 10 to the negative 13th. Now, if we have something like B, and I'm given hydroxide concentration, I'm probably going to go opposite log of hydroxide right away. And technically, I am calculating the pOH. Opposite log of 1.0 times 10 to the negative third. And that's hydroxide. So again, and you don't have to plug this into your calculator. If you understand the log log, it should be the opposite exponent of 10. The pH is, or I should say the pOH is 3. So options then. You could do this guy, pH plus pOH equals 14, and I should be looking at a pH of 11. Or you can do this. You can do hydrogen concentration times hydroxide, 1.0 times 10 to the negative third, molar hydroxide, equals 1.0 times 10 to the negative 14th. And then you could solve this for hydrogen. Well, this would be fun. The hydrogen concentration is 1.0. Oh, what do you know? Times 10 to the negative 11. And then I could go opposite log. Well, this just seems like a lot of work, doesn't it? But I at least want to show you it's an option. Then you could go opposite log of 1.0 times 10 to the negative 11. That's the hydrogen concentration. And either way, your pH is 11. To be honest with you, when I usually teach this to first-year kids, I teach them the second method. It's kind of mean, isn't it? I never show them pOH because I kind of want them to understand that second equation. I want them to understand that if you know the hydrogen or hydroxide concentration, you can solve for the opposite using that equation, hydrogen times hydroxide equals 10 to the negative 14th. Now, obviously, this solution is more basic. The pH is 11. And if I compare the two concentrations, well, yeah, there's a lot more hydroxide as opposed to hydrogen. The hydrogen concentration is very low. Another example. All right, this one's going to ask us for everything. The pH of a sample of human blood is measured to be 7.41 at 25 degrees. Notice, too, that they're listing at 25 degrees because that whole, like, hydrogen times hydroxide equals 10 to the negative 14th, that was measured at 25 degrees. That is an experimental value at 25 degrees. We want the pOH, the hydrogen, and the hydroxide concentrations. Okay, so let's do the pOH the easy way. We know that pH is given 7.41. That's my pH. Plus pOH always equals 14. So all I have to do is subtract, and I get my pOH. How about 6.59? All right, there's one. Let's do that the easy way. The hydrogen concentration. People always kind of forget about this. If you know the pH and you understand logs, you can figure out the hydrogen concentration. The log log is just the exponent of 10. pH is the opposite exponent of 10. So all we got to do is say 1.0 times 10 to the negative pH, the 7.41, the opposite of the pH. Now, technically, this would not be listed as a final answer. If you were doing this like multiple choice or free response or something like that, this would not be the final answer. We'd want to simplify this. It's a little taboo to leave a decimal as your exponent. So you just plug it in your calculator. Just plug it in and go 10 caret negative 7.41, and out pops your new answer. We would put the answer as about, I don't know, 3.9-ish times 10 to the negative 8. There's the hydrogen concentration. I mean, obviously, like once you simplify it, you're going to get something times 10 to the negative close to negative 7.4. But now your exponent will be a whole number, and you'll have a decimal out in front, and that's okay. That answer is more acceptable than 10 to the negative 7.41. So just be aware, if you were especially doing multiple choice or something, you would not find that as an answer. It would be simplified to about like 3.9-ish times 10 to the negative 8. What else do we need here? Hydroxide. We have two options. Option number 1. You could do something similar. If we know the pOH, we can use that in the same way to calculate the hydroxide concentration. We can say 1.0 times 10 to the negative 6.59. We could plug that in our calculator and simplify it then. How about 2.6 times 10 to the negative 7? Molar hydroxide. So you could do the same thing. Use your pOH, the opposite log of the hydroxide concentration. Or your other option. Or you can use this guy. If you calculated the hydrogen concentration, 3.9 times 10 to the negative 8, there's the hydrogen. You could multiply by hydroxide, and the product should be 1.0 times 10 to the negative 14th. Either way, you should get the same answer. So just be aware that all of these equations are given to you in the packet. pH, pOH, hydrogen times hydroxide equals 10 to the negative 14th, as well as that pH plus pOH equals 14. So practice a couple of these in the homework, but this pH stuff should maybe ring a bell.